Let's start this. I'm going to start the broadcast now, and then I'll welcome everyone and then hand over to you.
The broadcast is now starting. All attendees are in listen-only mode.
Welcome. Welcome everyone to today's IOActive webinar on SATCOM security. I would like to introduce you to IOActive's Principal Security Consultant, Ruben Santamarta, who will be presenting today's webinar. We have 30 minutes for today's talk, following which we will go into a Q&A session, which will take place on Twitter, or if you do have questions, you can email us, but we'll have more details on that, which will follow at the end of this presentation. But for now, let me hand it over to Ruben to kick it all off. Ruben, over to you.
Thank you, Craig. Well, thank you everybody for attending this webinar. I know it's maybe some complicated days, so thank you for attending. It's really appreciated. Okay. Well, today we are going to talk about SATCOM and how you or your company can identify the threats or the vulnerabilities that you are exposing through your SATCOM systems. So basically, our goals for today is first of all, introduce SATCOM. We are going to see the common scenarios where these kind of terminals where these kind of terminals are where these kind of terminals are deployed. Also, we'll explain how is the IOActive approach to evaluate SATCOM security. We'll see some of the results of this research, and finally we'll see how vendors reacted to this research and the current situation. Well, IOActive was founded in 1998. It's privately owned. We have acquired several companies, including the Argenis from Cesar Cerrudo, FlyLogic, which was a hardware security company, and we have quite a few people working, consultants working all across the globe, almost 100 consultants from different countries. And we recently opened a state-of-the-art hardware research facility in CRL, including garage and lab with cars from various manufacturers. Well, this is the agenda we've got for today. We have some introductions, methodology, vulnerabilities, reactions. Well, I'm not going to say anything new about satellite communications. Probably all of you know that because of the terrestrial limitations, we need to rely on satellite communications to perform critical operations. These kind of terminals are used by different sectors. For example, the maritime, industrial, the military, or aerospace, emergencies, or even media. So basically, the satellite communications infrastructure can be divided into two major segments: the space segment and the ground segment. Our research was focused on the ground segment, where specifically all those devices, we can say the mobile earth stations or satellite terminals that are used to access the services the satellite provides. For example, we can see how satellite terminals are used in the military. In this case, the terminal is the Harris RF 7800 began, which used the Inmarsat for constellation. So you can see that the different units of in this case the U.S. Army, use this terminal to communicate with additional units to ask for help if they are facing a critical situation, and this terminal allows them to overcome the limitations of the radio equipment, which usually is limited to the line of sight distance. So another option or another scenario is the media. For example, the Hughes 9201 terminal is widely used among the media. In this case, BBC journalists in Ukraine. And one of our targets also is used in the aerospace sector, even for military aircraft. In this case, the AVIATOR 700G SATCOM equipment. The vendors affected are the big players in the sector. We have Iridium, Inmarsat-C, Cobham, Harris, GRC, Hughes. So let's move to talk about methodology. At IOActive, we have a holistic approach. We are highly motivated by the outcome of our research, and these results can be extrapolated to every single layer of our approach. So the expertise, the knowledge we gain by researching into hardware is also feeding the software layer, also feeding the wetware layer, because we are also working of offering services for social engineering or physical security, and finally the intelligence services, where we provide our services in terms of intelligence. So in terms of threat modeling and risk analysis, there are several steps that should be taken into account. First of all, we collect information about how your company is operating, because it's really important to understand how your company is really working on with the different vendors, the different actors that are involved in your everyday processes. Sometimes the attack vectors and the attack surface is not as obvious as you expect, so it's surprising when you find some attack surfaces that you don't expect. Also, we always try to identify, characterize, and evaluate the assets you have or those you are considering to deploy, because it's really important to save money, time, and efforts to perform an evaluation of those assets or new systems that you are considering to install or deploy, because otherwise you have to wait till the new system is already deployed to perform the evaluation. And in this way, probably the outcome is that you have to redesign the system, because probably the new review will uncover some risk or will uncover some vulnerabilities. So we always recommend a proactive approach in terms of reviewing what you are planning to deploy before deploying it. And basically, what the results of our work is that you can back your decisions on technically accurate reports and realistic expectations. In the specific case of SATCOM, we used static analysis to approach this challenge. Basically, SATCOM equipment is used on board aircraft or vessels, or used inside a military facility. So this basically means it's almost impossible to have physically access to that equipment. But this doesn't mean you can't research into those devices. So our approach is basically based on two main points. First of all, the information gathering stage, where we collect every information we can find. We have data sheets, multimedia material, videos, presentations, pictures, anything. We also have success cases. Companies upload to their websites, manual, press releases. Everything is really useful to try to understand how the system is working without having physical access to the system. And then when we have collected enough information, we move to the reverse engineering stage. We don't have access to the equipment, but we do have access to the software and the firmware. So that is enough to analyze the security of these devices. And that was what we performed in this research. Basically, we collected the documents and we mapped every feature into the code, into the firmware. In that way, we could evaluate all the functionalities they were documenting. But our focus wasn't to find vulnerabilities or common vulnerabilities, or for example, integer overflows or buffer overflows or something like that. But we were after the usual design problems. So we can divide the findings into four major groups: the hard-coded credentials, backdoors, insecure protocols, and undocumented protocols. So basically, we were trying to understand how those devices were working. We can start by talking about air. To put things into context, the ARIN 664 standard describes the aircraft data network. There are four different domains. For example, the passenger information and entertainment services and the passenger-owned devices that share the same purpose, which is basically entertain the passenger. But on the other hand, we have all different domains: the aircraft control domain and the airline information services, which are intended to provide support for more critical operations, either for controlling the aircraft or to perform an airline different operations. So we have that within an aircraft. There are several domains that have different criticalities. But the interesting thing is that all those domains share the same SATCOM equipment. In this case, the SDU and the SBU, which stands for Satellite Data Unit and Satellite, Swift Broadband Unit. It's worth mentioning the special conditions document that the FFA published some years ago in order to address the network architecture of the Boeing 787. The highlighted part is the response from Airbus. Basically, they say that, okay, if we have to prevent any potential or malicious changes, and we have to physically separate all the domains within an aircraft, there are several things that are not going to work anymore. For example, the SATCOM, and it's basically what we have been saying just a minute ago. So one of our targets was the AVIATOR 700D product, which is used within the aviation sector, is developed by Cobham. So this product is comprised of the different components. We have the Swift broadband unit, which, if you see the schema, poses a clear attack vector because it has a built-in Wi-Fi router, and it's connected, or it's intended to provide connectivity to the in-flight entertainment network, also to computers network on board the aircraft, and it's also connected to handsets. So the built-in router, the built-in Wi-Fi access point pose a significant attack vector. So we try to understand how the different security functionalities were working. For example, we found this one. The man-machine interface security that the engineers implemented is obviously almost non-existent. For example, the SBU can be configured through a web interface, and if we take a look at how the security of this web interface is implemented, we see that unless you are authenticated, properly authenticated, or the functionality requires a connection to the maintenance port, and this port is not connected because the maintenance port is intended only for specialized staff from the airline or from the vendor to connect to fix problems or to upgrade the firmware. So basically, if you are not authenticated or you are not connected to the maintenance port for several actions, what they are doing is adding a disabled attribute for the HTML. So basically that's useless because it's client-side security. So you can, even if you are not authenticated, you can perform any operation you want. But for example, in terms of the MMI security, all the products that support configuration through the web interface have the same vulnerability. They have an administrator password, and if you forget your administrator password, you can ask for a reset code. So in order to ask for that reset code, you need to send your IMEI number, and also in certain cases you have to send the serial number as well. So we were reverse engineering the firmware, and we found that they are generating the reset code and comparing with the reset code the user entered. So obviously we can replicate this algorithm, which is pretty simple. They are using a hard-coded string and then the MD5. For certain products, the algorithm is a little bit more complicated, but still it can be replicated. So by exploiting the previous vulnerability, we can become administrator, we can achieve administrator privileges in any product. But the SDU, it's an interesting component, but the SDU, the satellite data unit, can be considered the core of the SATCOM equipment on board an aircraft. In this case, the SDU is connected to critical components on board an aircraft, for example, the MCDU, and it can be controlled through this device, but this device is located in the cockpit, so it doesn't seem possible to access the cockpit. But it's interesting because you can also configure the SDU through a handset, but you need a PIN because some functions are restricted. According to the documentation, there were 3 different levels of authentication. We have the normal user, the super user, and the service provider. But when we looked at the firmware, we found a backdoor. So, for example, in the slide, you can see the yellow basic block, which is the backdoor authentication, and on the green basic block, you can find the legit authentication. Basically, they are working in this way. The backdoor generation, in this case, we are analyzing the proper authentication mechanism. Each PIN is locally stored. It's transformed through a series of logical operations, and then to avoid generating the same number for the same PIN, they use the serial number of the SDU to generate a different one. Also, when the user enters a PIN, it goes through the same algorithm and then through a comparison. But for the backdoor, it's totally different. The PIN is always that number you can see there, and the serial number is backdoor, so they are adding a new factor, the 24-bit address of the ICAO, which is basically an ID that every registered aircraft has. So all you have to do is replicate the algorithm. You obviously need to know the 24-bit address of the target aircraft, but it's not very difficult to obtain that information. So by generating this backdoor, you can perform privileged operations against the SDU. For example, you can shut it down, and you can modify settings, which basically is a potential risk. And let's talk about C. Well, our target for the maritime sector was the Sailor family of products, which are widely deployed. Some of these products are required to be installed in certain kind of vessels because of the international regulations. So it's something that poses a serious risk. So The Global Maritime Distress and Safety System is a series of procedures, protocols, and different types of equipment that are intended to increase the safety of vessels and the crew, obviously. So, as we said, for certain vessels, this kind of equipment is mandatory. For example, if the crew is facing a critical situation, they can send a distress call, so the emergency services can attend that request and send help. So within this system, the satellite infrastructure plays a vital role. Some of the targets we compromised belong to this console, this GMDSS console. Long time ago, the International Maritime Organization released some recommendations when developing this kind of equipment, and you can see that, for example, in November 1995, they said that this kind of equipment should be protected against the effects of computer viruses. So, okay, so the cellular product use a protocol to connect the different components, so they can detect new devices on the network, or they can update the firmware. Obviously, the ability to remotely update firmware in one of those devices is very interesting from the security perspective. So we try to reverse the protocol, and we discovered that this protocol is basically a mix of SLP and SNP without any security at all. So in order to, for example, to update or install malicious firmware, basically we have to create a malicious firmware, set up a TFTP server, send the proper SLP request to discover our target device, and then send the specific SNP request to set the TFTP server from where the target device will download the malicious firmware, set the file name, and then set the download control variable to a specific value in order to trigger the firmware upgrade. And then it's over. The only thing we need to know is how to craft a malicious firmware. So we reversed a specific binary I found in the firmware in order to understand how the format of this firmware was working. Basically, it's a simple format. You have a magic, and then you have a series of streams. With every stream has a header with a class ID, the header size, the body size. Everything is checked by using CRC. There are no digital signatures, anything. So obviously, you can create your own malicious firmware. And in several conferences, we performed a live demonstration of how to install a malicious firmware. In this case, we created a slot machine. So instead of the proper functionality, when you press the red button in order to send a distress call, you obtain a slot machine. But another interesting thing is how we hacked into the Inmarsat-C transceiver. We see that the crew use this terminal to these GMDSS consoles to send distress alert, to receive data from authorities, to receive different kind of information that may affect the safety of the crew and the vessels. So that was an interesting attack vector. So the first thing we found was, as usual, several hard-coded accounts, but in this case it was even more interesting. The documented ones were normal, super, sysadmin, and distributor. There were a couple of undocumented credentials, the production and the developer, apparently. We could retrieve the password from the firmware in a function that was intended to reinitialize the default data from the manufacturer process. Another interesting feature of this Inmarsat-C transceiver is that it supports a remote message. If they detect the messages that this transceiver is receiving, and if the transceiver detects a specific kind of message, which the first characters are TOTTEAC, then that means that that kind of message is over-the-air command. So this kind of command should be authenticated, but again, there is a backdoor that can be used to bypass this authentication. So, they are using the hard-coded credentials, but they use a trick to prevent everyone using the same password. So what they are doing is encrypt the hard-coded account with the PCB number, which is a kind of serial number that is unique for every Inmarsat-C transceiver. But again, the encryption is not real encryption, it's just a series of logical operations, and we can replicate the algorithm to generate our own password. There are different commands implemented. We can modify almost everything. We can modify settings from the SIP security alert system, which is a system used to send distress calls when the crew is facing a terrorist attack or an act of piracy. So it's pretty bad. But another interesting thing we are going to publish shortly is the ability to perform attacks against the own Inmarsat-C infrastructure. When you can compromise an Inmarsat-C transceiver. In the picture, you can see the basic architecture of the Inmarsat-C system. We have 4 main components. We have the LES, which is the land earth station, which is basically a gateway between the mobile earth station and the ground infrastructure. And we have the network coordination station, which is in contact with the LES, and it's intended to provide several services to release or to lock channels, to assign channels for the communications. But from our point of view, the problem is that, as we see in this slide, the trust boundary relies on the fact that the end user is supposed to not control the Inmarsat-C transceiver. The problem is that we are controlling the Inmarsat-C transceiver. So in this way, we are opening the door to several attacks. If you can see as you can see in the slide, there are several important IDs that identify the different components within this infrastructure. We should focus on the forward ID, which is a 6-digit number that is used to identify communication from the less perspective to the mesh. And the return ID, which is basically the same structure, a 6-digit ID, which is used from identify communications between the mesh and the less, from the mesh perspective. So by reverse engineering the firmware, you can see that you can spoof these values. You can potentially send malicious data back to the system on the ground segment. For example, the Inmarsat-C supports data polling and data reporting that is used to provide SCADA services for vessels. So you can basically send malicious data to those systems. You can handle requests intended for other terminals. You can impersonate different mobile earth stations. So it's pretty bad. You can also perform other kind of attacks, denial of service mainly, because they are using slotted Aloha for the communications. So there are certain timeouts that certain intervals that every terminal needs to follow in order to not block all the slots. But in our case, we can ask for resources, so you can basically perform the denial of service attack against the satellite infrastructure. Another interesting case was the Iridium case. Every vessel that deploys Iridium Pilot or Iridium Open Port product is connected in an internal private network operated by Iridium. This product can be configured by the operator through a web interface. The problem is Iridium can also configure that product from their side using those credentials you can see there. Also, we found a way to update the firmware. So a potential attack or a potential scenario is where you install a new firmware with a malicious client-side exploit that targets the browser of the Iridium operator. So if the Iridium operator connects to your product, you can attack his browser, and once you have access to the Iridium network, you can access any other Iridium terminal. So again, it's not a good idea to put or to deploy or implement this kind of security strategy. And let's move to some reactions from the vendors. For example, Cobham acknowledged that the command or the vulnerabilities were in their product, but well, they say that you need to be in the same segment of the network. So, well, I don't think it's really a problem. Iridium said that they weren't going to fix that. So, well, Hughes acknowledged that they have backdoors and hard-coded accounts, but under their point of view, this is not a problem. Just in case of clarification, I mean, when I say that it's not a problem, I really mean to say that it's not a problem to be on the same network or on the same segment. You don't need physical access to exploit that vulnerability. So I don't completely agree with the response we had from Cobham. This one is also interesting. They say that backdoors are common these days, but it's not a problem. Well, it's their opinion. We always recommend the different approach. But well, not everything is bad. We have received a really positive response from different companies and institutions. This research raised awareness through media coverage, so that's a good thing. Now everybody is aware of the potential threats to this kind of equipment. And recently, I read in the news that the several organizations, international organizations, united to increase the safety of aircraft and aviation in general against cyber threats. So fortunately, things seem to be changing. So it's over. If you want to ask anything, just please use this hashtag, or feel free to send an email. Also feel free to ping me on Twitter if you need any further clarification. So thank you.